Hello, in this video we are going to summarize functions that we need to use to implement BFS in Python. The first thing that we need to do is to import DQ. So we say from collections import DQ. Then we need to define a variable as our Q. We say Q equals DQ and make sure to put this parenthesis. So our Q could have multiple scalars in it. The way that we can add a scalar is to append it to the end of that. We say Q dot append and then we put that variable in it. So let's say that is called I here. So that is a scalar. And usually after we add something, what we do is that we are going to pop left from the queue. And we usually have a while loop. In that while loop, we are going to take out all of the nodes from the queues one by one. We say while queue, and then you want to pop left. You say s equals q dot pop left. And also we need to keep the track of the visited nodes. For that we use the data structure set. We say scene, for example, a variable could be at the beginning an empty set, and then if you need to add that, for example, after you pop left, you just say scene dot add s. Also our queue can have a structure that in each node of that we could record a tuple. So for example here each tuple has 3 scalar values in it. So for example you can see I have scalar, scalar, scalar. So this tuple is one node of the queue. This happens, for example, when you are searching a grid and you also want to preserve the time. So in that case, for example, you are going to say, I'm going to append R as the row coordinate and C as the column coordinate, and also I want to add T for time. So in that way, I can add these 3 to queue as a tuple. Also, we usually add the same thing to our set. And when you want to pop left, that is similar. So you say R, C, T. And function is same thing. And then for the add, you just can say, for example, add R, C, and T. This is very useful when we are searching a grid. The next thing that we do in BFS is usually to go and search around the R and C. For example, if we have a grid, we can use something similar to this. So we say for neighboring R, neighboring C in 4 directions of R and C. And then we usually have a condition to make sure that our neighboring R and neighboring C are in the bounding of the grid. So for example, R is the number of rows and capital C is the number of columns, and we say if nr is in the bounding and nc is in its bounding, and then the condition that the problem states, though maybe the grid at that location should be 1, and then usually we check if that is not in our scene, and then you can go and append that to your queue and go forward, and visually increment the time here. So it could be a timer here that you can increment. And this is very common way of solving a BFS solution when we have a grid. In searching tree using BFS, for the data structure queue, we can have nodes of a tree added to that. For example, we can have node 1, 2, or all the way, for example, to node 10. Different nodes of a tree be in our queue. And then we usually start with adding root as one of the nodes of a tree to our queue, like this one. And then while queue, when you want to pop left, you just say node equals q.popleft. And this node is a node of a tree. It has all of the information about a node. Information like value and left and right children. And sometimes you are going to use BFS and search the tree, but at the same time, we need to record information about that node. For example, what is the depth of that node? In that case, we can use tuples. For example, in this structure, we have node 1, depth 1 as a tuple, and then node 2, depth 2, all the way to the end, node 10, depth 10. And when you want to append, it's just a tuple. You use the q.append. And when you want to pop left, that is similar. You just say node depth. Okay, this is pretty much the summary of BFS. And thank you so much again for watching this video.